Okay, good morning, everyone. Everyone for whom it is morning. Good evening, good night for people in places like Seoul and Tokyo. Um, our audience is on Zoom and YouTube, so I can see who's I can see who's on Zoom. At the moment, nobody's in the Zoom meeting, so I'll give it until 5 minutes after the hour here in New York City. Meantime, I've put the agenda up and shared the screen, so you should all be able to see that. I'll say it in the PowerPoint, but I started these meetings to kind of have a two-way discussion about a book that I and two co-authors are writing. The book will be about model risk management. The reference is in the PowerPoint. And it'll be the first textbook about MRM, which we think is pretty important. In fact, last week we discussed some other textbooks that have come out since the SR 11.7 guidance in 2011. There are books, none of them textbook, and unfortunately, none of them is comprehensive enough for everything that we feel should be covered. At the bottom of the agenda, you'll see I put my email. Delta Vega is my own consulting company, and I've worked for the likes of Morgan Stanley, Jefferies. I mean, I'm available to work at any of the large Wall Street banks in New York City. Although most of the last year I've been focusing on the textbook and on setting up my own Airbnb here in Brooklyn. For some reason, I couldn't find the link to the LinkedIn profile. Uh, but I seem to be the only Jonathan Schechter PhD. The difficulty with spelling it is that you have to observe that there are 9 letters in the name and that there are 2-letter H's, which at least to English speakers looks wrong. It looks like the second H should not be there. Uh, I can go into that if anyone has any questions. It's because it comes from Hebrew originally, and the way it's written is in a Germanic way. So in Jewish parts of Brooklyn, in Germany and in Northern Europe, Schachter is always spelled correctly. In Southern Europe and the rest of the world, it doesn't look right. Okay, coming up on 8:05. In fact, it's 8:05. So good morning, good evening, and good night to everyone. This is the 13th of a series of mermaids. Mermaid stands is how you pronounce MRMD, which is Model Risk Management Discussions. Today's focus is going to be the SS123 UK Model Risk Management document released by the Prudential Regulatory Authority, the PRA, and now being implemented in the UK. And something beeped. I'm looking. Anyway, my name's Jonathan Schachter, and the date and time are up there just in case you're watching this on a recording. So here's the general introduction. Welcome to everybody. Everybody is welcome to participate from anywhere in the world that you can get on the internet. No invitation is necessary. And you know, things obviously are done in English, and the book is being written in English. The book I'll refer to later, but I'm happy to look at you know, putting things in other languages to make people understand things better. So a couple of points. This obviously is a Zoom, so you're free to participate on that if you want to be interactive. If you just want to see it kind of read only, then you can go onto the live stream, which is in the LinkedIn appointment. It's the Delta Vega channel on YouTube. And then finally, I discovered recently, actually, it was it was my co-author who's a lot younger than me and therefore has a lot more technological capability. And he showed me that you can take minutes in a Zoom, or rather, Zoom itself is taking minutes using AI. So that's kind of useful. Right after the meeting, I'll distribute the PowerPoint, the minutes, and then the live stream link. So there'll be paper trail. So yeah, so the one reason to discuss the UK SS123 MRM document is that this is all in the context of and motivated by a book that I'll refer to. I believe it's on the second slide. And so the UK essentially, more than 10 years after the canonical Federal Reserve Board 2011-7 document, sometimes just called 11-7 or SR 11-7. So this is essentially a UK reworking of that in some sense, but I'll highlight the key differences and things where I think the PRA, the UK in general, has added some important content. Obviously, if you're going to be doing mathematical models in finance across different countries, you'd certainly like to, have something that's consistent between the US and the UK. In the book, we talk about other standards. For example, Abu Dhabi. So UAE has, the some standards of its own. The Japan has some rather weak standards that seem to be just a clone, a bad copy of, in my opinion, of SR 11-7. And but there's also the ECB. There's also the German regulator BaFin. I think there should be things out of the Hong Kong Monetary Authority. There's Australia has something, and I know Canada does. So, and other have, other countries have standards. I my Another co-author says that in Mexico, the validators really have to be deep in the weeds in the sense that they have to really be able to run the models, not just replicate them. That's my understanding. And then the topic I'll spend at least half the talk on is standard errors. Just the whole idea from my physics background of you don't just quote a observation like the period of the pendulum. You also quote the uncertainty associated with it because, these are, remember, random variables that we are getting an expectation of an expected value now. And so therefore it's just a snapshot. What we really want to know is if we do it repeatedly, what would be, let's say, the sigma, if you will, in that measurement. And this comes about in statistics because it's finite n. That is, we don't have an infinite number of data points. In fact, in finance, we often may only have, one a day for a year, so 250 data points. That's enough to make something asymptotically normal if the underlying is relatively well behaved. But higher moments, as we will see, including skew and kurtosis, are fairly questionable until one gets to very large numbers. So the next time you see a skew in a report based on 250 daily observations, you can treat it with a good bit of skepticism. Not going to say it's wrong. Okay. And then finally on this list, I give my contacts. So let's then go to the PowerPoint that I wanted to discuss today. And this will summarize everything. Let's see, go into the slideshow. Right. Okay. So as discussed, the topics for this are the PRA document SS123 and the standard errors of the first four moments, essentially, of a distribution. Just to put it out there, I'm in Brooklyn, New York. I believe I mentioned in passing before. So first of all, I think I said a good bit of this already, that it's called Mermaid. Here's the actual textbook reference itself right here. So, the name, sorry, you can't do that in slide mode. Anyway, I'll put so it's coming out in academic press in 2026. In particular, we're going to start submitting the manuscript. Although we have the contract, we will start submitting the manuscript starting December 1st. So please reach out if you're interested in getting some advance notes on it. We have about 20 chapters, and some of them have been sent out to colleagues for review. We strategically want to have comments in by the December 1st submission so that we don't run into intellectual property questions of who owns the material after that. So if you have some time this summer, this fall, it would be helpful. I can send you a table of contents so that you could pick and choose what you might be interested in. And then this MRMD has two functions then. So, for example, today I'll preview some of the book content on standard error in a chapter called Statistics Refresher, refreshing your mind on statistics, or teaching you if you didn't get it to this depth. And then we can certainly bring in, current topics of interest. SS123 is certainly something like if you're a Big Four consultant working in the UK, you are spending a lot of your time working on SS123. And I know that because my colleague who's working on it is a Big Four consultant who works for UK banks. Okay, so we're going to talk about PRM maybe for 5 or 10 minutes, and then the skew kurtosis, et cetera, for standard errors will take maybe 20, 30 minutes. And I'm going to end sharply at the top of the hour in New York. That would be 9 a.m. So let's go. Okay, so as I discussed briefly in some comments on the agenda page, this is in the spirit of the canonical Fed document SR 11.7, which was essentially very much motivated by the great financial crisis, notably by the failure of the Gaussian copula to describe CDOs properly. So we went from the ordinary, what they teach you, don't put all your eggs in one basket, diversify. That's usually said with regard to allocating cash in a portfolio, of course. But in this case, it's almost like an allocation to models. And one of the questions we address in the book is, do managers, does the CRO really know what models are being used and how frequently they're being used? And could they, for instance, look and say, oh my God, 50%, 75% of our positions are using all the same model. So that's kind of undiversified as to model space, if you think of the model space as being isomorphic to the space of portfolios. I think there's basically two things. I'll cover them in the next two slides. One of them is that the PRA document SS123 has a lot of definitions in it, which SR 11.7 does not. I would say in many ways they reflect and back up what's in SR 11.7, but where the things are implicit in SR 11.7, they're explicit in SS123. And then I know that there's a number of concepts. One of the things about that slide you'll see is that there's sections there's principles, there's subheadings, so that it's almost like, I don't know, the U.S. Constitution or maybe the tax code in the U.S. Everything has a section, a subsection, and so on. So I think in some ways it's easier to use. It would be easier to use for a bank examiner and perhaps easier to use for a model validator and people who oversee that. The contrast is that SR 11.7 just has, five, I believe it is, broad sections and no subsections to speak of. They certainly have itemized lists and things, but you would have to point to a page number or something if you said, you're not in compliance with this and this. So first of all, some definitions. So believe it or not, the Fed does not really define what a model owner is. It doesn't define what a model risk control is, and so on. I include business decisions here because, Wall Street's a business, hedge funds are a business, anything in finance is and economics is potentially business. And so that is driving things. I mean, after all, in the SR 11.7 document, it says you need to pay your validators a pretty good compensation, a pretty good salary, so that they're rewarded for good validation efforts. So business is always a part of things. Then I referred to key concepts. Model inventory, I'm not exactly sure why that's blank, but there are a lot of things in the model inventory. And again, that's something that's addressed in the chapter on model governance in our book, which I've spoken about before in these and as part of the live stream archive. So we don't have a statement like this in SR 11.7. What is the purpose of or the primary responsibility of model validation? As far as tiering, the ones at the bottom, okay, so here you can see all the subsectioning. So I could say, if I were an examiner, you are in violation of principle 2.3 in section 4. And these things here, they're all mentioned in SR 11.7, but here they are called out and itemized, if you will. So I think it's useful. That's pretty much everything I wanted to say about that document. The current plan is to have a spreadsheet in the book which compares across these jurisdictions of the UK. I mentioned UAE, Japan, and Canada, and other entrants that perhaps we don't know about. As I said, the Hong Kong Monetary Authority, I'm pretty sure, my co-authors are pretty sure that they take model risk seriously, but I've yet to see any document like that. Okay. So now let's switch and let's talk about specifically real samples that are done anywhere in social science, anywhere in science particular. And the number of things in the sample is generally not infinite. It may not even be 100,000 or 1,000,000. As we know in finance, there are 250 days in a year. A look back of 5 years is still just a few thousand. So the numbers are small. Now, I did physics. I did astrophysics as my first career. Happy to talk about that. But everything in physics has an error bar. Everything from the pendulum experiment that some of you may have done in freshman physics to, we were measuring properties of black holes and things like that. They all had some understanding of, how well do we really believe this number that we just observed, given that it's an expectation value of essentially a random variable or an uncertain variable, even if it's deterministic. So I've said this, and again, the bottom of the page, most financial series are I wouldn't say really low end. It's more than 100. It's enough to make something asymptotic Gaussian if it's fairly well behaved. But that does not necessarily mean that all the moments are significant, as we'll see. So the coverage, the agenda then is to talk about 5 moments: mean, standard deviation, VAR, variance, the skew, and the excess kurtosis. Remember that a normal distribution has a kurtosis of 3. And so excess is, with 3 subtracted from it. And I also include, because we've been talking about it in some LinkedIn discussions, one fairly extensive, what's called the coefficient of variance. So this is just a measure of the size of a distribution, the variance of a distribution in relative terms, in terms of the mean. So instead of variance in the numerator, we simply have the standard deviation. And then in the denominator, we have the absolute value of the mean, because certainly, 1% over a negative mean is the same thing as a 1% over a positive mean in terms of, relative variance. It's a ratio, so it has some problems. Later, I will tell you that to do the numerical experiments, I had to take mean equals 1, even though the standard normal has mean equals 0. Well, mean equals 0 is not going to work too well in the denominator for experiments. Typically, we'll see if things like the mean is 1, the standard deviation is 1, the skew and excess kurtosis are around 1, then it's easy to understand. So then you have something like, if the standard error was something like 0.05, that means it's a 5%, reliability. And again, you can think about this as, if it were drawn from a normal distribution, then we could talk about the sigma. And we could say, for example, that 2 times the standard error, standing in for sigma, is like a 95% confidence number for a normal distribution, or asymptotic normal. And then by corollary, if you have a kurtosis of 1, but the standard error is 2, that's not a kurtosis. That's statistical noise. Okay, so I'm going to take the lower moments first. And in all these, we're thinking about a sample of x1, x2, and so on to xn. All right, so what we need in this statistically is what are called the UMVUEs. Those are the uniformly minimum variance unbiased estimators. And then once you have one of those, then you can say, what's the standard error in that? For mean and variance, it's pretty much what you would expect. The arithmetic mean here on the left, and on the right over here, this is just what you would expect. It's a central moment, so you subtract off the mean that you've just calculated. But these are both, based on data. They're sample mean and sample variance. Standard deviation, because of the square root, is more complicated. I think most of us know about Jensen's inequality and the properties of convexity. So, for example, its estimator is not just the square root of what I just presented for the sample variance. Generally, the way it's written, and the references in the book, is as the product of S, which is the square root of the sample variance, times Kn. And this is when it gets a little complicated. This Kn quantity is written in terms of it's dependent only on n. S, of course, embeds the sample, as we've said, the sample standard deviation variance. So the gamma functions are here. And in fact, the ratio of 2 gamma functions like that for the n's that we're talking about, you'd be better off using the exponential of the difference rather than the ratio. So that's what the approach we use in the book. And, Python has a gamma function. If you're not familiar with it, it also has a log gamma function. So that was Kn. which you'll see appears here in the final formula for standard error of standard deviation. And there's another quantity, which is Vn, which is this, which is essentially the, a component from the sample standard deviation. Again, it's better here. So here it's the gamma function value and then squared. So using logs is the preferred way to go and the accurate way to go for computation. So we covered, so here's a table of all the SEs, which I will discuss in the next few minutes. As you can see in this column, it's what is it that we're doing the statistic of. So the sample mean, the sample variance, this KNS quantity I just discussed, and then these are the sample skew and sample kurtosis. So the only two things that are really in here are N, as you would expect. And for the first three, essentially for the first two moments of the distribution, the sigma, the sample standard deviation is included. For the higher moments, and we can get into why that is, as it says here, there is no sigma dependence. So the skew is only dependent on N. All right, so let's see what happens. What we're going to do is we're going to use a normal distribution. The standard normal has a 0 mean and 1 for its standard deviation or variance. We're going to use 1, 1, just because if we're talking about percentage changes and things, we want to have reference to something that doesn't blow up like 0. So there are 5 charts. Each chart is going to have the value on the y-axis. So in this case, I know theoretically that the mean is 1, right? I just said it. But this is what you calculate from random numbers in Python for 10 samples, 50 samples, 250, 1,000. This is the financial range. And then for very large, which you usually don't have in finance. So you can see even for mean, there's some uncertainty if you only use 250 or 500 in your sample. Is that ever quoted? No, of course not. There is no error bar in finance. Similarly, for standard deviation, and that's with that formula with the gamma functions, here SD is equal to 1. And here, it's similar behavior. In both cases, it does convert to 1 at higher, but again, even at 250, there's uncertainty in the standard deviation that you would quote. Just do it quickly in Excel and say this is the answer. But management really should know that there's an error bar associated with that, and you don't know that number, except to plus or minus a standard deviation. In this case, I said 2 standard deviations equivalent to 95%. For simplicity, these error bars are 1 SE, so equivalent to 1 standard deviation, which I think is normally the convention for, let's say, a physics lab report. Before I mention the coefficient of variation, since I'm still talking about the first 2 moments, let me introduce the concept of the relative standard error, SER. So that just means that it's normalized by the statistic itself. So this would be like the SE of the mean divided by the mean. Again, another reason to make sure that the mean is 1 or a number other than 0. So, in the standard way, relatives errors add in quadrature, right? As we know. So therefore, the standard error of this ratio is the quadrature sum of the standard errors, the relative standard errors of the 2 underlying quantities, which remember are X bar, the mean, the sample mean, and this UMVUE of the standard deviation. So after we do that and we know CV, then we can calculate the, if you will, the with units, the standard error, not the relative error of CV, the coefficient of variation, excuse me. And so you have a similar chart. In this case, the CV is 1 and does do that asymptotically. Here it's actually pretty wide for 250, and you say that's strange. But of course, when we add things in quadrature, then we're going to get a larger number. So the next time you use coefficient of variation, again, you can use it, but use an error bar. Now, what about the higher moments? So in this case, in the previous examples, I used a normal distribution, which we know has a mean and a variance, and has a non and has but has zero skew and zero excess kurtosis. So to go a little bit beyond that, you can use what's called the skew normal distribution. It's available in Python. It's called skew normal. Imagine that. And in this case, the location and the scale are the equivalent of saying the standard deviation. The scale is the standard deviation like thing, and the location is the mean like thing. So you can't unfortunately tune it to the skew. Or if you like, you can solve a sixth order polynomial, and I can give some information on that. It's one of the problems or maybe one of the problems in the book, but it's not easy to solve a sixth order polynomial like Newton-Raphson doesn't work, so that you can't really back out the parameter that you need to put into skew normal to get a skew of 1. However, here theoretically, I know that the skew is 0.851, and correspondingly, here's when I try to measure it, and it shows a similar pattern. Again, maybe a bit worse. I think it might be hard to convince me of some of these things. This is supposed to be 1 right here, but you can see the measured value is 0.8. And so, sorry, it's supposed to be 0.8, and it is around 0.8. I got confused between this and the previous. Anyway, but there's still quite a bit of variation in there that could be done by repetitive samples. And I would argue that in the case of kurtosis, here the theoretical value is about 0.7. It's worse. I'll give a rough estimate, but you can see even at 10,000, you can see a little bit of the error bar here. How many financial samples have 10,000 data points? Not too many. Yeah, so wrapping up on this slide for the SE, if you take those formulas, this is a homework problem in the book, and you multiply them out, the ones for skew and kurtosis. Let me just go back to them. So these are just polynomials in N, and you can see that nicely they essentially are like 1 over N, right? For example, this is a quadratic polynomial in N, and this is a cubic. This is a cubic, and this is a quartic. So at least we know that it's going to be a decreasing function as N gets larger. In the spirit of that, what you can do is, and this is the homework problem, you multiply out these, and then you apply L'Hopital's rule repeatedly. And so that is getting you the large N behavior. And again, we're imagining that the distribution is asymptotically normal. So therefore, we can apply this. And then the expressions turn out are fairly simple and good to use as a rule of thumb. So the skew, for example, is in the large N limit when L'Hopital's rules applies. As N goes to infinity, it looks like the square root of 6 over N. So here's this 1 over N behavior as expected. And in kurtosis, the coefficient is 24 instead of 6. So what that means is, given the fact that skew is usually around 1, right? Skew, I've seen a rule of thumb that plus or minus 1 in skew is a noticeable skew, or maybe significant, but this is really the significance argument here. And excess kurtosis is also not going to be very much past 1 or 2. there aren't too many leptokurtotic distributions in finance that have a total kurtosis of 10, so an excess kurtosis of 7. Um, so, so that you could back this out. Like, let's say you want a 5% on a measurement of unity for skew. So then you can see directly from this that you would need, about 2,500 data points to do that accurately, and almost 10,000 to do kurtosis to the same 5% significance if the underlying quantity is around unity. So, essentially it's this slide and thinking up to it that makes me very dubious going forward, having looked at this in detail for the book, on what is a skew, what is a kurtosis as measured in a financial data set, and can you actually believe it? All right, so I'll let that sink in. It perhaps might be useful to, what else can I show and tell here? Um, I can't really show you very much in terms of the first part of the talk, more about the book. I can page through some parts of the book itself, especially this chapter on statistics refresher. Well, you don't need to see this probably. Oops. Okay. I'm a boomer, so moving the stuff around on the screen is not always that easy. But if we go directly to that statistics refresher chapter, essentially I wanted to communicate the message, and this later chapter backs up some of the things we say before, is that you have to be very careful in terms of believing something, especially if it's a higher moment. Correspondingly, if you measure a mean or a standard deviation or a correlation, that may be affected by the fact that there's skew and kurtosis that you don't know is there. So, for example, there's some charts. I'm not sure I could find them, but that my colleague Martin Goldberg put together, my colleague and co-author. And in those cases, you can show that the correlation between two variables will increase relative to the base case of skew equals 0 and excess kurtosis equals 0. If you add that, then the measured correlation will actually be an overestimate of what the correlation would be if there were no skew and kurtosis. I can try to find that later. This is just, I'm paging through the book, but you can't see it. So yeah, let me try to find correlation in the manuscript. It might be around here. Yeah. So for example, let me put this up. This is a nice chart. If I can get it up there with my boomer dexterity. So the correlation that you observe, let's say you start with two variables that are correlated to 61%, two normal distributions with no skew and no excess kurtosis. And then on the x-axis, we're applying some skew to one of the two variables, x, and on the other one to y. And it's pretty much symmetric, but you can see that, what should be 61% can get very low. Can get as low as 0.35 if the skew is extreme enough. So you can put this together with the discussion I presented earlier. You certainly want to see if there is skew there and whether it's significant. It would be even possible, Martin, who created this graph, we talked about this yesterday, to create an error bar for correlation or in the language we've discussed this morning here, an error bar for covariance. So everything in the covariance matrix. So the but there's some obvious problems with that, and this is similar to the difference between logistic regression, which is typically used like for probabilities, so that the response has to be limited to between 0 and 1, because like it's a probability of default. Correlation is itself, as we know, restricted to -1 to 1. So you need some sort of a transformation. Martin recommended Box-Cox, so that let's say you start with a distribution of correlation. I mean, correlation definitely could be distributed in some sort of distribution. One thing I'll show is, if I can find it, there was observed correlation that over time of Japan and let's say a stock index, but it's all over the place. There it is. Okay. So I also want to emphasize that these are all Pearson and so-called linear correlations. If you do this with rank correlation or the non-parametric versions, Kendall's tau is another one, then you actually are fairly robust to skew and kurtosis changes, or the presence of skew and kurtosis. But you can see, that correlation's unstable. It's not stationary. It's all over the place. If you do it as a function of time, there's no time index here, but I think these are daily data over a year or two. But yeah, so that's that. And then let's go on for a couple more minutes. If I look at CV, that will probably get me to so here, if you like, here's the section in the statistics refresher where we present a few more facts. Like this is the canonical form of the skew normal distribution. It's a product of an ordinary normal and something with an alpha parameter that controls the skew, although not in a direct way. That's why I had to come up with the funky numbers for skew and kurtosis. Here's the table I presented before. So one homework problem is just to do that, and the skew normal distribution is presented in that first homework problem for the chapter. For the next one, it's applying L'Hopital's rule, and then the third one is what I talked about, which is the coefficient of variation and the application of that and the quadrature sum of the two relative errors. All right. So I think with no questions coming in on email, double check one more time, with currently nobody else on the Zoom, I will do what I said. I'm going to cut the meeting right here and give everybody back a little bit of time. So we hold the meeting to about 45 minutes. I think the usual attention span of a human being or of a quant. And look on LinkedIn for the posts on the minutes and the PowerPoint and the link to this as a live stream on YouTube. So thanks very much. Have a good rest of your day. Be that a good evening, a good night, or a good morning. Thanks, and we'll see you next week here at 8 a.m. Tuesday, the 27th, 8 a.m. New York. Stopping the share, signing off.